All right, and just a warning, we've gone through like all of these markers this morning. They're all terrible. So if you can't read anything, just let me know and I'll try to say it to you because I've been going through all of them and they're no good, and I have no new packages of markers either. So.
We might have to just skip it.
All right, we're going to try this red at first and we'll see how this goes. So this example 1, calculator is permitted. We're letting f be a function with 5 derivatives on this interval from 2 to 3. Assume that this fifth derivative, so this is that n plus 1 derivative that we were talking about yesterday. So this fifth derivative, and in your paper, do you have 0.2 or 0.3 there?
0.3.
Okay, for this example, the work I have, we're actually going to use 0.2. So this bound, what we're saying, this fifth derivative within this interval has a maximum value of 0.2. That's the upper bound that we're going to be using. We know that fifth derivative is no greater than that 0.2 within that interval. That's given information. They're just telling you that. For all x in the interval 2 to 3. So that's what I was just explaining there. And that a fourth degree Taylor polynomial, T4 of x, for f at c equals 2, is used to estimate f of 3. So ultimately what we're doing, we're trying to find an estimate of f of 3. They tell us that we have a function with 5 derivatives. So we're using a fourth degree Taylor polynomial. So that upper bound that we're talking about, we have to look at the fifth derivative, that one term past it. All right, so part A says, how accurate is this approximation? Give 4 decimal places. So what we're trying to find is f of 3. And this says we're using a Taylor polynomial, not a Taylor series. So this T4 of 3, is this equal or is this an approximation? Squiggly or equal sign? It's a Taylor polynomial, not a Taylor series. So which is it? The series has the infinite terms, so the series is equal. But if we're using a Taylor polynomial, we have a limited amount of terms, so it's an approximation. It's close, but not exactly. So we want to know how accurate is this approximation. So from yesterday on the previous side of the page, we're going to use that remainder formula, the Lagrange error bound, or the Taylor approximation. So R4, because fourth degree, and we're trying to approximate at 3. And we're going to use that formula from yesterday on the front. So it was that absolute value. On the top, remember it looked like the Taylor series, but there were a few differences. On the top, it was that n plus 1 derivative, not the nth derivative. So that's this 5, or f of 5x that they're talking about there. So the absolute value on top, f5 of z. Remember, that's some z value that we don't know. If we knew what the z value was, we wouldn't have to approximate it. Over 5 factorial. They told us we're trying to evaluate it at x equals 3. They gave us that, so the x value is 3. They told us the center is c equals 2, so minus 2 to the 5th power. Again, we have that formula that's similar to the Taylor series, but we actually know what the x value is, and this is the n plus 1 derivative, not the nth derivative. And again, it's the absolute value of all that. So now, they told us this part here, we don't actually know the actual value of the 5th derivative at this some z value. But they told us within that interval that we're worried about, from 2 to 3, the upper bound of this derivative, we know the derivative, 5th derivative, is no greater than that 0.2. That's the greatest it is within that interval. So we're going to replace this part with 0.2 because that's the greatest it can be. So absolute value of 0.2 over 5 factorial. 3 minus 2 is just 1. So 1 to the 5th power. So now when the calculator comes in handy, go ahead and solve that and figure out what the remainder or the error is for the 4th degree Taylor polynomial within that interval. Anybody have any decimals out there? Again, it says to 4 decimal places. And again, what this part A is finding, it's asking how accurate this approximation is that we are trying to find. So this value that we're finding is the maximum error of our approximation. We know it's no greater than this value. What is that value that you found? Yeah, I have .0016 is what I have here. I'm not sure what the other decimal was. Did you get 0016 or 17? Is that what everybody got?
One was like 6 repeating, but it's
Okay. I'm going to use 0016 for terms of this problem, but 0017, not far. Anybody not get that? Alright, so that was just asking how accurate the approximation is, give 4 decimal places. So we're saying we're within this amount. So part B now, we're going to be able to use that error, maximum error, to find our interval. So it's telling us, with this 4th degree Taylor polynomial, we don't actually have the polynomial, but they're telling us if we plug in 3 to this Taylor polynomial that we're talking about, you get this value, 1.763. Again, we're trying to approximate at 3. So it says use your answer from part A to find the interval in which f of 3 must reside. Again, remember this is an approximation number. We don't know exactly what it is, but we do know the maximum error. So that's why we're trying to find the interval in which our actual number is. So f of 3 is found within, we have 1.763 minus our 0.0016 to find our lower bound of the interval, and then 1.763 plus 0.0016 to find the upper bound of the interval. So this new bound is 1.7613 and 1.7646. So again, I know that's hard to read. 1.7613, 1.7646. So we know because of that upper bound they supplied us with, this was the maximum error we could have. So we know for certain that f of 3 has to be within that interval. This is our approximation, 1.763, but the actual one is within that interval. That's all they're asking for part B. Part C and D, they're just going to ask some general questions about the interval that you now found. So they're going to say, if f of 3, could it equal 1.768, why or why not? So is that possible? Could your answer be 1.768? I see some head shakes, and I agree. No, because why? What do you notice? Yeah, it's out of the interval, it's out of bounds. So no, since 1.768 is not in the interval, and we're going to specifically say, so if this was like an open-ended response on a test, no, since 1.768 is not in the interval from part B. That way they know exactly what you're referring to. They know that you're talking about this interval right here, and that's what you use to find your answer. All right, letter D. Similar to C, could f of 3 equal 1.761? Why or why not? Well, if you look at your interval, yeah, we could not have it in the interval because 1.761 is not within there. It's 1.7613, so no, it could not be in there. So we've completed the first problem with Lagrange error bound. Again, they gave us an approximation of the fifth derivative telling us the error bound, so that's what we used. We didn't actually know what the fourth degree Taylor polynomial is, but they gave us values of the fourth degree Taylor polynomial. So we didn't have to calculate anything with it. They supplied us with those. And we used the Lagrange error bound from the previous page, which I said we didn't derive, but that's something you could look up on how it's derived. But we used that formula, which is a manipulation of the Taylor series, to find the maximum error of that fourth degree Taylor polynomial. Okay. So example 2 is similar. It's going to be the same type of problem, just a different function. So if we're ready to go on to example 2, any questions? All right, let's try example 2 then. Again, calculator permitted question. So again, this problem is about approximating sine of 1. And we want to know how accurate our approximation is. So part A, find the fifth degree Maclaurin polynomial for sine x. So in that first problem we talked about, they just told us we were dealing with some fourth degree Taylor polynomial. They gave us some information, said that T4 of 3 was some value they gave us. In this one, we're actually going to use the Taylor or Maclaurin polynomial for sine of x. So the first one, they didn't actually make us use a specific one. They gave us information. In this example, we're going to have to actually use the Taylor polynomial for sine of x. So it says a fifth degree Maclaurin polynomial for sine of x. Then use your polynomial to approximate sine of 1. And use Taylor's theorem to find the maximum error. This right here, Taylor's theorem to find the maximum error. This is, in other words, Lagrange error bound. So these two things are interchangeable. Taylor's theorem to find maximum error. That means Lagrange's error bound. So it can be asked two different ways. So you need to be aware that that means Lagrange error bound. For your approximation, give 5 decimal places. So they want us to find that same value we did in part A on the previous problem. We want to go to 5 decimal places though. So find that maximum error. So before we start, we know we're dealing with sine of x. So we need a fifth degree Maclaurin polynomial for sine of x. What is that Maclaurin or Taylor polynomial for sine of x? Think about the characteristics of it. What does it start with? Think about the powers, the signs. It's on a note card that you had filled out. So sine of x. How is this polynomial written? Well, that would be the last term of a ninth degree Maclaurin series. We want to go to the fifth degree.
But isn't sine only includes the odd numbers?
Yes, that is true.
Would it not be the ninth degree because of the ones that are missing in between?
So whenever they talk about fifth degree, that means x to the fifth is going to be your last one. They don't necessarily mean 5 terms. If they're asking for a series, they'll say, give me 5 terms of the series. So you would have to list out 5 terms. But if they say fifth degree polynomial, well, the degree, 5 is your highest degree if they're asking for a fifth degree polynomial. They're not asking for 5 terms, fifth degree. Okay? So sine of x, what's the first term? Is it an x or a 1? It's x. Remember, Eric said it's an odd polynomial, odd powers. So x to the first is the first one. Now again, this is Taylor polynomial, not series. So it's not an equal sign, it's an approximation. Again, first one is x. We know it's odd, so we're going to go to x cubed, but do I have a minus or a plus? Minus. Remember, this is an alternating one. Minus x to the third over what factorial? 3 factorial. This, if I would stop here, this is considered a third degree. Okay? I don't have 3 terms, but this is a third degree because the highest power right now is 3. They're asking for a fifth degree. So it's alternating plus x to the fifth over 5 factorial. So just to review back a few sections, this would be a fifth degree Taylor polynomial for sine x. Again, those series that we had written out, we had plus dot dot dot, and that represented an infinite amount, which would be equal, but this polynomial is just an approximation because we're limiting the amount of terms. So just try to keep those straight, okay? So again, that is sine of x, just generally. But again, we're trying to approximate sine of 1. So sine of 1. So again, everywhere there's an x, we want a 1. So again, use your calculator, find out the approximate value of sine of 1 using a 5th degree Taylor polynomial. Again, it's not exact, this is our approximate. Go to 5 decimal places, please. Anybody have a value? Yep, I think we just rounded differently on the last one, but yes. I do. 0.84166 or 67. Again, in the grand scheme of things, that one decimal place isn't going to make a huge difference. You have the correct answer. So 0.84166. Again, this is what I'm saying my approximation is. So what I'm going to do now, I'm using Lagrange error bound or the Taylor's theorem to find my maximum error. So I'm using the next term. So I need to use, since I'm at a 5th degree, finding the error for the 5th degree at 1. And again, I have to use the n plus 1 derivative. So I'm at 5, so I need to use the 6th derivative of sine because I'm using the n plus 1 derivative. So absolute value of f of 6 of some z value over 6 factorial. Again, this is x minus c. What is the x value I'm trying to approximate? What x value am I trying to approximate? 1. So I'm going to have 1 minus the center. The center is what? McLaurin would help you out. What's the center? 0. So it's 1 minus 0, so I'm just going to put 1 to the 6th power. And I forgot to put in here, this f of 6 of the z should be in absolute values also. So the absolute value of this 6th derivative at some value z. Again, this is the value that maximizes the derivative. So I'm going to draw, well, let's first find the derivative. So if I have, you can include this anywhere on your page, I'm going to write it up top. If the original f is sine x, what's the first derivative? Because we can physically find out what the 6th derivative is. What's the first one? Okay, we have cosine x. Second derivative would be negative sine x. Third, negative cosine x. Fourth, sine x. Fifth. So lastly, f of 6 is what? Negative sine x. So we know that's the derivative we're dealing with. We know within this interval that we're talking about from our center 0 to 1, because we know the x value we're trying to approximate is 1, the center is 0. So from 0 to 1 we're trying to maximize that 6th derivative. So if you think about it as a picture, I'll draw a picture here to start. Coordinate plane. And we think about sine. Well, this is negative sine, so it's going to start at 0. It goes like this and back and forth. So that would be negative sine. And we're going from 0 to 1. So on sine, that's somewhere around there from 0 to 1, this portion of sine. So visually, this is what we're trying to look at. We need to think of a value that would maximize f of 6 here. But if you think about this, we're taking the absolute value of that. So all these values, if you're taking the absolute value of that, it's really flipped over. These values are all positive now. Does that make sense? I don't want to jump too far ahead of. We're looking at this. This is the 6th derivative. But again, we're looking at the absolute value of the 6th derivative. So any of these values here are actually positive. Somebody get the door, please. All right, so if we have the absolute value of this, again, think these values are now going to be positive. At this value of x equals 1, that's where the value of sine is going to be the greatest. Because again, it's the absolute value, so whenever you take all these values and make them positive, this value right here will be the greatest value. Does that make sense? Why that value would be the greatest, taking the absolute value of it. Okay, so we're going to say, is it okay if I erase this picture? Does it have some room? Eric, you have a question?
So
I can tell you have a question.
At x equals 1, so you take the absolute value as the largest?
Yes, because we're just looking, at this portion right here. Okay?
Oh, okay, so we're not looking at the...
Because our interval that we're dealing with, we want to approximate 1. We know our center's at 0. So we're only looking at this little bit here.
So our interval that we look at is only from 0 to 1?
Yes, because we're trying to approximate 1. We know the center's at 0. So from 0 to 1, we're trying to find the greatest value of sine. That way we know our error is at the most it can be. Okay? But if I take the absolute value of this part, this is going to be the greatest value. You're good now? Okay. Any other questions? It was a good question. All right. So I'm going to erase this now, or try to. All right. So I said that sine of 1 is going to be the greatest thing. So we have the... Yeah.
It says, can you explain why, so you already took the absolute value before that, but you took the absolute value after that. It says z is an x value on the interval that we're looking at 0 to 1 that maximizes f of the 6th derivative, which would in this case be 0, and then you take the absolute value of that. Why don't you do it like that? Because the absolute value is outside of there. It's not on the z or something.
That's a good question. Trying to... Yeah, when I'm looking at that, the way I had understood it when we were doing it, you have the absolute values on that 6th derivative. So I had taken all the values.
That whole thing, including the absolute value, has to be the highest number possible.
Yeah, so I took the absolute value of my 6th derivative, looked at all my values, and I know when I take the absolute value, the highest value I can have on that interval from 0 to 1 is going to be at that 1 position. Because, let's see. Because I'm trying to maximize that derivative. I know that if I take that f of 0, and we saw that was right at the origin, if I take the absolute value, that is going to be the smallest value.
Yes, but we're maximizing the derivative, not that entire top function.
Well, remember too, there was a portion we had talked about where we didn't use absolute value. We said we could have negative and positive answers, and that would tell us whether our error was more negative or positive if we over or underestimated. So taking this absolute value is just making everything positive. So if you don't take the absolute value, you want to look for either your highest or lowest value. But taking that absolute value allows everything to be positive. You know your error is within this certain amount, and you don't have to worry about that negative.
So what you're saying is that it's not trying to make f of n plus 1 the greatest, it's trying to make that whole numerator.
Yeah, it's making it the greatest because taking that absolute value there is just allowing us to say that we know the error has to be under this value. If we don't take the absolute value, we're going to get a plus, or we could get, well, in that case it would be a negative number. So if you don't take the absolute value, that's going to tell you whether you're over or underestimated. But at this point, we don't care whether we're over or under. We just care about the interval that we're within. So that's why we're taking the absolute value. We get that value, the greatest value. So at that point, we don't know whether it was over or under estimated because we took the absolute value of it.
Okay.
Does that help a little bit? Okay. So that sign of 1 is the greatest value. And again, we said it was negative sign. We're going to take the absolute value again. So it doesn't matter whether you have the negative or positive. So I can include negative sign because that was the sixth derivative. So negative sign of 1 over 6 factorial 1 to the 6th. So again, we have values here. And this is a calculator question again, so you can use these to evaluate. So again, Eric, actually the way I had written it here talks about like this was going to give you a negative value.
Yes.
So technically, when I looked here, this was just visually, so I could represent in my head what's the largest value that the derivative can be at that point. So here's in the case, I wrote negative sign of 1, so I'm going to get a negative value. So technically, I didn't use those absolute values there. Like you said, we have another absolute value. This is going to change positive no matter what. So that gives you that negative, I believe that gives you negative 0.84147. So when you think about the absolute value, that's going to be a positive value, obviously, but that's the greatest potential it can be. We talked about negative or positive. But again, I didn't care here because, again, at the end, I'm going to take the absolute value again.
Yeah, my question was just, like the other day when you explained it, you made it sound like you were supposed to maximize the derivative. But here you're saying you have to maximize the entire numerator, correct?
Well, you're trying to, well, the numerator is the derivative.
The numerator is the absolute value of the derivative.
Yes.
Okay.
Yes. All right, so did anybody find a maximum error value for that? 5 decimal places? Go ahead.
0.00117.
Yep. 0.00117. So again, right now what I'm saying for this part A, I used the 5th degree Maclaurin polynomial that I had memorized. I found the approximation at 1 of the 5th degree, and I'm using the Taylor's theorem to find the maximum error, or Lagrange error bound. I know within, or for that 5th degree, my error is no greater than this value right here. This is the greatest possible error for that 5th degree Taylor polynomial. So part B, I'm going to use this answer from A for my interval to find my lower and upper bound of the interval. So again, I know my value, my approximation was 0.84166, and I can subtract that error, 00117, and I can do 0.84166 and add that error to get my upper and lower bound. So I can now guarantee after finding the maximum error, because we know we found the maximum possible value the derivative could have been within that interval, we know that our answer for the approximation of sine of 1, the actual answer, has to be within these two values. Again, we don't know exactly which value it is, but we know the actual is within these two values. So part C, could sine of 1 equal 0.87? No, because 0.87 is not in the interval from part B. So the two examples we did today, the first one, they just provided us the information. We applied the theorem. For this one, we had to use past knowledge that we have of Maclaurin and Taylor polynomials, of some of the memorized ones we have, like sine, and then applied the theorem to it. And using that maximum error, we now know that sine of 1 is within those bounds. I mean, we know what the approximation is, but we know for sure it's within these two. Okay. Does anybody have any more questions? That's where we're going to stop for today. We're actually pretty close to the end of class anyways. We'll pick up with examples 3 and 4 tomorrow. We should be able to get through those tomorrow and finish up with example 5 on Friday.